This video is to introduce you to Module 5, Chapter 5 of your textbook, Synchronous Sequential Logic. Sequential logic describes a system built with storage elements otherwise referred to as memory elements. What a storage element can do is it can store binary data. In our case, that data is going to represent some type of information. What information it represents depends on the system that we're using, storage elements or memory elements. We'll also talk about the state of a sequential circuit. That state of the circuit is described by the information in the storage elements themselves. So if we look at a sequential circuit, it's a combinational circuit. It composes of a combinational circuit and these memory elements. We have looked at so far as a combinational circuit where we have inputs and then outputs. And the inputs go through some combination of logic elements and result in new outputs. In a sequential circuit, you have inputs and this present state going into your combinational circuit, and that creates this new state that gets stored in the memory elements. The output of the memory elements are the present state. So this dotted line represents the circuit itself, where we have inputs on the left and outputs on the right. The present state is internal to our sequential circuit, and it's the output of the memory elements. The new state is a combination of both the inputs and the present state. So to specify a sequential circuit, what we need is inputs and outputs and these internal states, but it's actually a time sequence of the inputs and the outputs and the present states. That's what we need to do to define or specify a sequential circuit. With our combinational logic, all we needed was inputs and outputs. We could represent that in a truth table. Now we're additionally going to need the internal state and what constitutes the time sequence. So when we talk about a sequential circuit, it could be a synchronous sequential circuit or an asynchronous sequential circuit. Both designs assume that all the signals are binary and they take advantage of the Boolean logic that we've learned so far in this course. Synchronous design assumes that time is discrete. So we have, for example, every 1 second or every 10 seconds. And we use a clock signal to define how to represent that discrete time. There's no feedback allowed in synchronous sequential design, no feedback of the combinational logic. What we saw being fed back was the output of the memory elements. This is important to avoid race conditions, hazards, and hazards in your feedback. Asynchronous sequential circuits, however, time is not discrete. The input signals that drive the circuit, at any instant of time, those signals can change, and the order in which they change is what defines the time sequence. So those storage elements are essentially the time delay devices. So that's the propagation delay we learned about. So the propagation delay of the logic gates is what we use to store the information. So it's a combinational circuit with feedback, and it has the possibility of instability. Possibility of instability. So again, asynchronous sequential circuits, we're really studying synchronous sequential circuits, but we're going to need asynchronous sequential circuits to build the synchronous sequential circuits. The advantages of asynchronous design is there's no clock skew. We'll talk a little bit later about clock skew. And it requires lower power. Only the signals that need to transition are those that are currently in use. So we don't need to have a clock toggling up and down and up and down. That uses a lot of power. Also, if we look at the worst case performance for timing constraints, that tends to be better. It has an average case instead of a worst case that we can use for timing constraints. Additionally, just the global timing issues across the system, it eases the need to design for that. And it's also migrating from one technology to another. In synchronous design, is very specific to the clock signal and propagation delays. So advantages of asynchronous design, sometimes we connect two synchronous circuits with an asynchronous circuit. The disadvantages of asynchronous design is it's just plain difficult to design due to the stability issues in that dynamic state, the feedback of your combinational logic. So there's what we call hazards or race conditions. They have to be removed, And our existing CAD tools need to be modified to be able to work with asynchronous design. So again, we're going to be studying synchronous sequential design. However, we're going to need asynchronous design to build our flip-flops. So we'll use positive feedback and combinational logic to build a D-type flip-flop. So as an example here, these are inverters, and this inverter has positive feedback, but there's an opportunity for metastability in here. It's a bistable circuit. So for example, we don't see any inputs in this circuit, but if Q is a 1, then the input to this inverter is a 1. The output of this inverter will be a 0, and then a 0 at this input makes Q a 1. So once we get into a stable state, it will remain there in that stable state. But what we said here is this is a bistable circuit, but it has a possibility for metastability. So what do we mean by that metastability? A good example of how to think of metastability, if we have a ball on the top of a hill, if it's sitting there at the top of the hill, it's stable until it's not. If we get a little gust of wind blowing this way, it's going to blow down there. If we get a little gust of wind going this way, it's going to go down there. This is our metastable state, and for a cross-coupled inverters like this, if we have 2.5 volts at the input, that's going to it could stay in that metastable state indefinitely if there isn't, for example, the gust of wind or something to pull the inputs from 2.5 volts up to 5 volts. That's for our CMOS logic, where if you remember, CMOS has a strong 4.8 to 5 volts for a 1 and 0 to 0.2 volts for a 0, logic 0. So just to zoom in here, our bistable element here, if our input is equal to a 1, our output then is going to go to a 0. If our output goes to a 0, the other input goes to a 1. So we have this back and forth. Unless we're in this metastable state here, we could be stuck here at the 2.5 volts and moving in either direction. So that's the danger of a possible instability in an asynchronous circuit. So we have to watch out for that. And again, an analogy of that is the ball sitting on the hill. That's easier, perhaps physically, to understand that if we don't have anything to move that off the top of the hill, it'll stay there in that metastable state. So again, in this module, we're going to focus on synchronous sequential circuits. But we will use cross-coupled NAND and NOR gates instead of the cross-coupled inverters. We'll use cross-coupled NAND and NOR gates to build our synchronous memory element. So the concept, if we just jump back here, the concept of this cross-coupled inverters is perhaps easiest to understand because we know a 1 has an output of a 0 and a 0 an output of 1. We'll take this concept and we'll look at NANDs and NORs to build a memory element. So again, our synchronous clocked signals, the storage elements, are only affected by discrete instances in time specified by the interval of the clock pulse. So if we look here, we've changed the circuit a little bit where instead of our memory elements, we wrote flip-flops. A flip-flop specifically means that the only way to transition this memory element is either on a rising edge, so here we have a rising edge of the clock, or a falling edge of the clock. This clock signal, you see it's periodic. We have a period here from this rising edge to this rising edge. It doesn't look like a 50% duty cycle. It looks perhaps like a 30% duty cycle. The duty cycle specifies the period, the percentage of the period in which the signal is high, a voltage high, or a logic 1. So the only way to get from this present state to the next state, right? The inputs can change, but the only way to change what's in this flip-flop is we need a transition of these clock pulses. So a storage element used by clock sequential circuits, that's what we call a flip-flop. It's capable of storing 1 bit of information, and the state of the flip-flop will change only on a clock pulse transition. So that's where the signal goes from high to low or low to high. The feedback loop is broken if the clock does not transition. And this is key. We'll look at this more later, but this is a key fundamental information. So concerns of synchronous design is clock skew, a difference in when the clock arrives to different parts of the circuit. We want all the signals to change at the same time. Ideally, right, that discrete time we want to happen at the same time in all the different memory elements in our circuit. So the data that we're storing in this flip-flop must arrive before the clock edge. And what we see here is we see a D. This is our signal D. D is at the input to this flip-flop, and it's going from a high voltage and transitioning to a low voltage, then it's transitioning high again. The clock is going to sample that. This shows on a rising edge. So this is just one edge of our clock signal. It shows two edges, but the rising edge is the transition that's going to create a change in our flip-flop, in our memory element. Change from our present state over here will change to the next state on this edge. So what we have here is a setup time and a hold time. That data must be stable a certain setup time before the clock edge, and it must remain stable a certain hold time after the clock edge. So in this case, this flip-flop would sample a zero, a binary zero, into this flip-flop as long as it meets the setup and hold time. So what we have to do, so these are timing constraints that are much more important in sequential design than in combinational logic. So in a synchronous design, the worst case performance analysis determines the speed of the clock. So the slowest critical path determines how fast that clock, the frequency, how high a frequency we can use. So optimization for all parts of the circuit becomes important. And if we just zoom in and take another look at it, we're going to look further at these timing issues, but this is the essence of a flip-flop, a storage element that only transitions on the rising edge of a clock. In this case, it needs the data input to the flip-flop. So if we consider this to just be one flip-flop, here's the input to this is our D, that's the D, and here's the clock, CK. We're going to use a little triangle here for clock. All right, so that's it, our introduction video. In the next video, we'll start building a flip-flop with asynchronous design of cross-coupled NANDs and cross-coupled NORs.